Physics in relation with astronomy. Physics in relation with astronomy. Astronomy. We have discussed the role of physics in different branches of science. Now, what role it plays in astronomy? So, astronomy is the oldest science. It is the oldest science. So, it started with the human race on this very planet, because at the beginning, since the inception of humans on this earth, they started to visualize this, to see the sky, and they tried to figure out the motion of planets, motion of stars, and so on and so forth. So the first detector they used it for observations were their eyes. They were observing the things with the help of their eyes. When we talk about the astronomy, it started with, you might be knowing, it started with what we call as the Big Bang. It started with Big Bang. So there are so many models of the universe. One of the models is Big Bang model of universe. Before Big Bang model, you were having so many models. One was the static model of universe, another was the pulsating model of the universe. There are so many models of the universe. But the most successful one was the Big Bang model. When it started with a singular point, the temperature was very high and the density was very high. So an explosion took place, or we call it pre-model, the event took place while the expansion of the universe started. The bang, Big Bang is basically a mathematical term. It is not what you know it is. It is basically, it was one of the astrophysicists. He was basically deriving the models of the universe. He got the scale factor S is equal to 0. He got S is equal to 0. That means that when the scale factor, the scale of something is 0, that means mathematics fail is there. So he said, oh, Big Bang. Oh, Big Bang. So this was the actual case. So we started that. Now we say that the Big Bang was basically the initial setup in the beginning of this universe. When the explosion took place, because of the high temperature at the time of the Big Bang and the very high density, we don't know what was the cause of that Big Bang. So from that, you are at start you are having only the radiation phase. So you are having no matter dominated universe. It was a radiation dominated universe. Dominated universe. Radiation dominated universe. Okay? But when the temperature cooled down, so your corpus, free corpus existed only at the time of Big Bang. Free quarks existed only at the time of Big Bang. When temperature slowed down, these quarks combined to form protons and neutrons. As you know, your proton is made up of up, down. Three quarks. And your neutron is made up of up, down. Again, three quarks. So, this we call as baryonic matter. It is basically the physicists and the logic applied by the physicists and the theories provided by the astrophysicists. They try to explain the Big Bang, which is the start of the astronomy is because of the Big Bang. So astronomy is the oldest branch of science where you try to explore what is happening in the cosmos. Cosmos means in the universe. You try to find out the origin and evolution of the universe. You try to first give some theories, then there are the people who try to modify these theories, and they give these theories are then supported by the observations. For example, earlier it was stated by that universe is static. Even Einstein said that universe is static. That's the matter-dominated universe, but motionless. But because at the time the Hubble had not given his what you call the Hubble's law, velocity of precession of galaxies move apart. It was not at the time when Einstein gave his model of universe. But when Hubble gave his model of universe, the people started thinking, oh no, universe is expanding. So we try to observe the astronomical objectives with the help of telescopes. You are having the small ground-based telescopes. You are having the huge telescopes like you are having MMT, multi-miller telescope. You are having one telescope at Arizona. You are having now the 30-meter telescope is coming up. So these telescopes are basically they are being invented by the theories provided by the physicists. Are you getting my point? So you are exploring cosmos, you are exploring the universe, you are exploring the astronomy with the help of physics. With the help of physics. That is how your physics is helping in your astronomy. For example, the telescope is used detector. I told you initially that the initial detector is wire the eyes with the help of which we can say, oh, this star is brightest star. This is the second brightest star. This is the third brightest star. This is because we call it as Hipparchus scale, the magnitude of stars. Okay, the brightest one is called the first magnitude star. Are you getting my point? So basically, it was the physicists who contributed to astronomy as well as the mathematicians, because mathematics and physics are very much correlated. They are interdependent on each other. So physics in relation with astronomy. So these detectors, now you are then after eyes you are having photomultiplier tubes, where you are getting the counters from the source, that means the celestial objects. Then you are having CCDs, charged coupler devices, that you are having in your phones. Okay, a small chip, a few to 10 millimeter, a few millimeter on each side, consisting of large number of small regions, which you call as pixel. What is the aim of pixel? Converts photon into photoelectron. This builds up a charge. These charges are then moved in some regimented way to preserve the spatial pattern of light falling on these chips, which is then processed by the astronomers to study at ease on their computers and all that. So this is all this is called the CCD. It is the invention at Bell Laboratories. Okay. So these CCDs, they are basically the physics is behind it. Your photoreceptors, they are basically you are having the pixel. What's a pixel? So your photoreceptors are acting like a pixel. Small picture element. Are you getting my point? So this is the relation physics, the role played physics in astronomy. Now you are having another topic is that what are the four forces in nature? What are the four forces in nature? We basically in technical terms we call interactions. Four interactions. What are the four fundamental interactions in nature? We are having four types of interactions or forces in nature. One is what you call as gravitational force or gravitational interaction. So what is a gravitational force? What is a gravitational force? It's the attractive force between the pieces of the two materials, pieces of two objects of carrying masses. Are you getting my point? Yes. But gravity is a long-range force. It is though weakest, but it is a long-range force. The motion of the planets that you observe is because of this gravitational force. It is because of the gravitational force. The whole universe is bound. You are having the solar system where your planets are revolving around the sun. Then you are having satellites. Satellites on each corresponding to the planets. They are also rotating. They are also having motion because of this gravitation. But this you cannot shield the gravitation. You cannot shield the gravity. Gravity exists everywhere in the universe. We cannot escape from it. Can we escape from gravity? No, we cannot escape from the gravity. It's a long-range force. But this gravity, it may be, you may say that it is existing because of the two objects that you are having some masses, the force of attraction between the two forces. But I say that the gravity arises because of geometry. Gravity arises because of geometry. When I say because of geometry, I mean to say geometry of space and time. Space and time curvature. Space-time curvature. Space-time curvature. If you are something, some space you are having, and at the middle you are having some dip. You are at the middle you are having some dip. So, or the space is curved. Suppose the space is curved like this. All the objects that are moving at the center of this curve, they are moving, they are rotating around like this. Okay. So that's why we say every galaxy is having a black hole at its center. That we call as active galactic nuclei, AGNs. We call them as AGNs. We call them as AGNs. So we say Milky Way is also having a, at the center of Milky Way there is a black hole that is sucking all the mass that is moving around it. Moving around. If you take a funnel, for example, you can see the funnel is something of a curved shape. The space is curved. Because of the curvature of the space, you are getting the geometry. You are getting the gravitation. The objects are moving around this slightly, around this, the whole of this funnel. Are you getting my point? So, gravity arises because of, this is one type of the force that you find. It's a very, very long range force. Very, very long range force. Then what is another interaction? Another interaction is electromagnetic interaction. Electromagnetic interaction. Both the interactions are basically, both the interactions are electromagnetic force. Both the interactions, whether you talk the gravity or the electromagnetic interactions, they are basically long range. They are basically long range forces, because electromagnetism is because of the fact. So when you are having some object that is you are moving an object in a magnetic field, what it will generate? The moving magnetic field generated is, what is Faraday's law of electromagnetic induction? See, when we say electromagnetic waves, we say electromagnetic waves are basically self-propagating. They are self-propagating. They don't require any medium to pass. For example, I am talking to you. I require a medium atmosphere so that you can hear my voice, because that is the medium. How about the electromagnetic waves? They are self-propagating. They are self-propagating. Once you are having a magnetic field, it will generate what you call the electric field. So in response, it will generate again the magnetic field vector generates electric field vector, again generates the, so the cycle goes on, cycle moves on. So this is also a long range force. Between the charged particles, you are having the electrostatic force. Similarly, between you are having the magnetic interaction between the magnetic force. Okay, so both the two are what we call as long range forces. Both are long range forces. Then is the third type of force that we call as weak nuclear force. Weak nuclear force. This weak nuclear force basically it is taking place, it exists in decay processes. For example, in beta decay process. In beta decay process, you are having, if I remember correctly, neutron, proton plus electron plus antineutrino. Antineutrino. See, one is what we call as neutrino, another is antineutrino. See, neutrinos are the highest, neutrinos are the massless particles. Massless particles. What do you say massless particles? Because they are hardly detected by anything. Neutrons are hardly detected by anything. In beta decay processes, our neutron gets converted into proton and electron with the emission of antineutrino. Antineutrino is basically put there to basically satisfy the equation, to conserve what you call the Chipinel charge. So neutrinos are the highest energetic particles, but the problem with neutrino is that they are hardly detected by anybody. They can move through my body, they can move through these walls. So that's why if you have to detect a solar neutrino beneath the earth, you dig a earth very deep, then you put what we call as I guess chlorine. So once a neutrino strikes your chlorine, you get an argon that converts into argon and some electron. So if you remember correctly the reaction there, that is the kind of reaction that I am talking to you. So that means that way we detect the solar neutrinos. Because the problem with neutrons, they are hardly detected by anything. You can say the gamma rays are the highest energetic particles of the order of 10 to the 20 hertz. This is the kind of energy they are having, very tremendous energy they are having. So very, very tremendous energy they are having. But neutrinos having more energetic, but the problem with neutrinos is that they are hardly detected by anything. So when you cannot absorb such particles, and how can you detect them? It's doubly difficult to do such particles. So this weak interaction, it is a short range force. It exists between subatomic particles. In subatomic particles, you are having leptons, hadrons. आपको बात आ नहीं मेरी समझ में? So this is what we call as weak nuclear force. See, if we combine weak and electromagnetic force, what we get? We get electroweak theory. It was actually predicted by Salam way back by Salam. Then Weinberg experimentally verified the particles responsible for this electroweak theory that we call as WZ bosons. So this weak nuclear force is a short range force. We cannot combine interactions. We can find the particles responsible for electroweak theory, that WZ bosons. Then we are having the fourth type of, that is strong nuclear force. So strong nuclear force is basically existing within the nucleus. It exists within the nucleus. In nucleus you are having nucleons. Like neutron-proton is a nucleon. Proton-proton is a nucleon. Neutron-neutron is a nucleon. That means these strong nuclear forces exists between neutron-proton, between neutron-neutron. That means these forces are then what? Charge independent. Had they been charge dependent, then they could not have existed there. So they are charge independent, but SIP independent. Because neutrons have its own spin. All the particles are having neutron and proton. They are half integral participant particles. They are not integral spin particles like photons, bosons. So they are half integral spin particles. So strong nuclear force, it exists within the dimensions of 1 Fermi, and above 1 Fermi is around 10 to the power minus 15 meters. So above this range, these strong nuclear forces become negligible. Their effect becomes negligible. So in nature, we are having four types of forces of interactions. One is the gravitational interaction. So it exists, gravitational force exists everywhere in the universe. Then we are having electromagnetic interaction, electrostatic force or electromagnetic force. So it is also a long range force existing between the charged particles. Then you are having weak nuclear force. It takes place in beta decay processes, whether you get the inverse beta decay or beta decay process. Okay. Then you are having a strong nuclear force exists between the nucleons. It exists between the nucleons. Nucleons are basically charged. Nuclear forces are basically charge independent, but SIP independent. Then comes in your syllabus, we are having what we call as the Nobel laureates in physics. Nobel laureates that our country has produced in physics. Nobel laureates in physics. Okay. So first, what is a Nobel Prize? The question arises before we discuss how many Nobel Prizes, Nobel laureates our country has produced in physics. We must know what Nobel Prize is. Basically, a well-known a well-reputed chemist, engineer, and a wealthy industrialist, Alfred Nobel, he accumulated a huge wealth. So when he died, his will was opened. His will was opened. According to his will, he has basically expressed that the wealth that he has accumulated, it must be given in the form of prizes in 5 categories. In 5 categories. These 5 categories were physics, chemistry, then physiology or medicine, then literature and peace. Later economics, I guess economics is added. It was added later, but it was not in the will of Alfred Nobel. So, as per his will, an amount should be given and a gold medal should be given to the people who contribute to humanity. They must belong to either physics, chemistry, physiology or medicine, then literature and peace and economy. So, but there is a question, the mathematics is left there. There must be a reason. Some say that basically Alfred Nobel, he didn't think at that time that mathematics is a practical science and it contributes to humanity in any way. That's one of the reason. Second reason was that there was already the prize for mathematics, Scandinavian this prize for mathematics. So that was another reason. Third reason was that some people say that he was having some rift with Gustav Raffler. Gustav Raffler was a great mathematician. He was a mathematician. He was having some rift with this guy. That is why he has not kept mathematics in the list. Some say that since Alfred Nobel was not having, उसकी कोई बीवी भी नहीं थी, he was having only a mistress or you can say girlfriend. So some say that the Raffler was having some relation with her girlfriend or mistress. That is the reason. That's why he has not kept the Nobel Prize for mathematics. These are all theories, but mathematics has a very great prize that is known as Fields Medal. So, coming back to my topic, so these were the conditions laid down by the Alfred Nobel. So, who must receive his Nobel Prize? It contains a gold medal, it contains a diploma certificate, and I guess around a $1 million amount. Maybe it might have some. The news was that they might have the amount बढ़ा दी होगी थोड़ी. Okay. So but now the question arises: our country, India, very rich in its diversity, in languages, culture. It's a multi-linguistic country, multicultural country. It produces great people. Okay, from Aryabhatta, he was a great mathematician. Then you are an astronomer as well. So then India is in a tradition of producing very good mathematicians, astronomers. So India produced great people like Rabindranath Tagore. He won the Nobel Prize for Literature. So similarly, there are Amartya Sen, he won the Nobel Prize in Economics. Then you are having in the biological sciences, 1 or 2 people I remember correctly. So how many physicists from this country have won the Nobel Prize? One was C.V. Raman. C.V. Raman has given Raman effect. He has given Raman effect. In the Raman effect, the wavelength changes or is being deflected if a light is allowed to fall on some molecules. They deflect the light, and due to deflection, the wavelength gets changed. There are what we call it increased frequency lines and decreased frequency lines. that we call as Stokes and anti-Stokes lines, not your scope this time, because this is a very basic, this is a heterogeneous group belonging to some commerce, some zoology, some other subjects, so not going into that detail. So he has given what we call as the Raman effect. Raman effect. He gave it basically, it was some Adolf, I don't remember the correct name. He was given the theoretically this Raman effect, but experimentally in 1928 he experimentally verified this effect, and he got Nobel Prize in 1930. 1930 he won the Nobel Prize for this discovery. You can have you know the Raman's category. People from chemistry background who are learning spectroscopy, they might have gone through Raman spectroscopy. Okay, so this is one of the important methods in spectroscopy. So Raman, he was the recipient of a Nobel Prize. Then another great son of the soil, that is Chandrasekhar. Chandrasekhar has given a Chandrasekhar limit in 30s. Chandrasekhar limit. So he was astrophysicist. So see what Chandrasekhar limit says. It says that if a mass of the sitar is say 1.4 solar masses. One solar mass is 2 into 10 raised to power 33 grams. One solar mass. That is mass of the sun. If an object, if a sitar that is in the, see you are having an infinite number of stars in your universe. You cannot count them. In every galaxy you are having, you cannot count the number of stars your galaxies, your Milky Way galaxy is having. So you take observations every now and then, you find so many stars. So if a sitar, but every sitar goes through the process of birth and death. Sitar is born from nebulas, case nebulas. For example, we are having a Horsehead Nebula right now, Orion Nebula. So basically, the stars they born from nebulas. These are the basic gases that start collapsing, that start contracting, and they form what you call the star. That starts the birth of a star. So stars, they do born, yes. They die, yes. It's correct. So a star whose mass is around 1.4 solar masses, around like our sun, its destiny is to become a white dwarf. Where you are having electron degeneracy and electrons. Usually the electrons will be in abundance there. Then if a mass of the sitar is between 1.4 solar masses to around 3.5 solar masses, if I remember correctly, then it may become a neutron star. You will be having neutrons made up of neutrons. We call it, technical term is neutron degeneracy is there. Then if this mass of the sitar is beyond 3.4 solar masses, it is destined to become a black hole. See, black holes are very difficult to observe. You cannot observe a black hole. Why? Because they do not emit an electromagnetic spectrum. You are having electromagnetic spectrum, it starts from gamma rays, X-rays, ultraviolet, then you are having visible, red, infrared, microwave, radios. So it does not emit any this spectrum. इस स्पेक्ट्रम में ये इमिट ही नहीं करता है रेडिएशन. What to say, what to do? So that means we are having indirect evidences of black holes. We are having indirect evidences of black holes, but black holes can consist. They do consist. For example, you may see that is one technical that we call as light curve analysis. You plot a magnitude versus time graph. So you see, if you are in a binary star, you can see in light curve the primary or the secondary one of the objectives curve is missing. From that you can infer, okay, the other black hole is there. It is eclipsing around a black hole. like binary stars. So black holes, they do not emit anything. They do not emit, nothing can escape from black hole. So that is why they are very hard to detect, very hard to detect, very hard to detect. See, we are having a one problem that we call as dark matter. See, in universe, all the chairs, all the countries, all the continents, all the galaxies, all the stars, all the pulsars, quasars, whatever you have found till date, it constitutes only 4% of the mass in the universe. How much? Only 4%. 96% is a dark matter, missing a dark matter. And dark matter, okay? Are you getting my point? So, this is the kind of problem. People are working here, research is going on dark matter and dark energy, which that counters your what you call the collapsing. See, the universe is expanding. Universe is at what cost? At what cost is expanding? At the cost of dark energy, okay? So that's a deep topic, I will not go into that detail. So Chandrasekhar, he won the Nobel Prize. He won the Nobel Prize in 1983. In 1983. These were the two physicists from India who have won the Nobel Prizes. Okay? So that means our country. See, you imagine one thing. India was independent in 1947. Chandrasekhar, though he was born in India, but he got his doctorate degree from Cambridge University. So he has not studied here. He was later having the citizenship of the USA. So, but being the son of this soul, so contribution goes to the country where he has born. So these were the two greatest physicists that India has produced and who have won the Nobel Prize. Nobel Prize is a very, very prestigious award in the field of physics, chemistry, physiology or medicine or peace and literature. People are, this Nobel Prize every year is basically the Swedish and Sweden, the Nobel Prize, the country from where this Alfred Nobel belonged to Sweden. Am I right? Okay? So, Nobel Prizes are given every year to those people who contribute in physics, chemistry and other allied subjects. But I am here precisely talking about physics. So, physics is a very, very vast subject. It is golden age started from 1905 when it was, before that it was what you call the part of philosophy as I told you. So now when Max Planck gave his quantization of energy concept, energy is quantized, it is not having the continuous spectrum as the classical physics predicted. For example, you are having hydrogen atom spectrum. For n is equal to 0, half of h nu. N is equal to 1, first state, 3 by 2 h nu. N is equal to, you have gone through the 12th class. That's why. So even at absolute 0, the energy is not 0, it's a 0 point energy. So this energy exists in quantas or bundles, and this energy is quantized. E is equal to h nu. E is equal to h nu, where h is your Planck's constant. This was the basically the revolutionary this concept given by the Planck for his explanation of black body radiations. Where he tried to explain what was the flaws with Rayleigh-Jean's law, what was the flaws with Stephan's law,